Okay, thank you very much. And Clotilde, you still need to send me your slide from last week. I'm not forgetting.
Okay.
All right.
Are you seeing my screen?
I see everything, yes.
Okay. So so I'm going to present you the distinguishable cluster, which is an alternative method to coupled cluster. And yeah, so the standard way to improve a coupled cluster calculation is by growing the number of excited states and reaching full CI. So first there is the coupled cluster double calculation, then CCSD, then the T correction, the full triples, etc., etc. But this is really computationally expensive, and we know that even for CCSD with the T correction, sometimes it fails when the single reference we use is bad. So for example, in dissociation processes, so since the start of coupled cluster, single reference coupled cluster, for example, has struggled with the dissociation of the N2 molecule. So we would want to develop other way to improve the coupled cluster calculation without without too computationally expensive approximation. So another idea is what Bartlett and his co-workers call addition by subtraction. So it would be great that if we remove term from our CCD or CCSD calculation, that we get a higher accuracy, because the computational cost would be the same or even less, but yes, with a better accuracy. So there is some example in those papers. For example, the parameterized CCSD by Huntington and Nugent, or Scuderia et al. Use the ring CCD or ladder CCD, and there is a correspondence with RPA. So there are a lot of examples and a lot of approximation, and one of those approximation is so the distinguishable cluster introduced by Katz and Manby. So in this paper from 2013. So the idea is to remove so the basic idea is that the exchange processes is a local interaction. There is no exchange between two distinguished particles, and so there is no exchange between two particles that are well separated. For example, if you have many particles that are localized on different sites, a distinguishable calculation can give good result, because they can't exchange because they are all localized. And so on this basis, they choose to remove the term involving exchange between different clusters operators, because they say that the inability to model how to say it. If you have a restricted reference, you can't localize the orbital, the atomic, the molecular orbitals on each atom during a dissociation. So you can't have a good exchange between those clusters. So they just want to remove them and to see if it's better or not. So here is the energy equation. So for the CCD approximation, and so the amplitude equation in its connected form. So the exchange between cluster operators need at least two operators. So we look to the quadratic diagrams. So for the CCD equation, there is 4 diagrams, so which are those 4. And we can, so this is that the B diagram is an exchange one, so they want to remove it. And also so that these are a Goldstone diagram. So the interaction vertex is a double bar integral. And so in this double bar integral, there is a Coulomb part and an exchange part. And we can see that the exchange part of diagram A will be exchanged between 2 operators. So they say that they want to remove A exchange and B. So yes, here that's not the same vertices. Here it's normal Coulomb integral vertices. So there is the Coulomb one and the exchange one. And so a nice property of a coupled cluster approximation is to be exact for n electron if the truncation is at the nth order. So here we are looking at CCD. So we want that the approximation is exact for 2 electrons. And so in the 2 electron case, we have this relation between the diagrams. And so we can just add so AX plus C over 2 to our amplitude equation, and it will change nothing. So by adding so those relation with a good parameter, we can rewrite the amplitude equation like that. So this equation is exact for 2 electrons, but we can use it for more electrons and just watch if it's good or not, but this will not be exact anymore. But they tried to see if it works, and so yeah, I didn't have time to copy the equation because I struggled with the LaTeX package to draw diagrams. But you can find the DCD, the distinguishable cluster double equation, next to the CCD normal equation in the paper from Ricci in 2016. So maybe I'll put the paper with the slide on the Git repository. But it's just the normal. It's just a normal CCD equation with terms that are removed according to this equation. So that's really not hard to code if you have a code for the CCD case. And so they studied, so this figure is from the paper from Katz and Manby. They studied the dissociation of the N2 molecule, and so CCSD with the T correction and CCSDT are all failing at a certain point, and we can't converge anymore those approximation. But with the distinguishable cluster double, oh yeah, I forgot, sorry. So they use Bruckner orbitals to because it allows them to not take into account the T1 operator, which involves or which makes the orbital relax. So they use already orbital that are relaxated. Sorry. So, and we can see that with the Bruckner distinguishable cluster double gives a qualitatively good result for this dissociation. And so they show other example where like the HCAT H4 molecule, sorry, and it is good also qualitatively in those models. So we see that with an approximation with less terms, we get results that are better. So that's really cool, I guess. And so there is many further studies on the distinguishable cluster, if you want. So after they studied the effect of orbital relaxation by including the T1 cluster or by using orbital optimization as Fabrice presented. After they studied the explicitly correlated method, and also in the paper from Ricci, they studied extensively the dissociation of N2, and they showed that with a UHF reference, the CCSD is gives the same result as a distinguishable cluster, because with a UHF reference, you are able to break the symmetry and then to localize the orbital on each atom. And so there is no more the bad exchange effect or the exchange effects that are, not well modelized between two cluster operators. So, yes, it's that.
That's it. Thank you,
Yes.
Antoine. Is there any question for Antoine?